In this lecture video, we're going to look at what is called a structural regression model. This is a particular type of structural equation model. Here's an outline of what we'll be looking at in this video. We'll first describe the example and provide the context for what we'll be looking at. We'll then specify the structural regression model as a system of statistical equations. Finally, we'll specify the structural regression model graphically by creating a path diagram for it. So let's take a look. Let's first describe the example. Consider a structural regression model to determine the relationships between two fluid intelligence components, induction ability and figural relations ability. Induction ability during the junior year in high school and figural relations ability in each of the junior and senior years are considered to be latent constructs or factors. According to a proposed theory, three manifest variables are indicators of induction ability, three manifest variables are indicators of figural relations ability for the junior year, and three manifest variables are indicators of figural relations ability for the senior year. To specify the model, we'll go through these 5 steps. Step 1 is to identify all latent constructs and manifest variables comprising the SEM. In step 2, we specify an equation for each one-way explanatory predictive relationship in the SEM. In step 3, we specify notation and/or values for the variances of all random variables in the system, as well as for all covariances of pairs of random variables in the system. Step 4, we identify all model parameters to be estimated, and then we'll count them. And then in step 5, we'll construct a path diagram for this structural regression model. So let's take a look at step 1, where we identify all latent constructs or factors, as well as the manifest variables comprising this structural equation model. In this model, we have 3 latent constructs, and you'll recall that latent constructs are unobservable characteristics. Latent constructs are also called factors. We'll denote the first factor by F1, and this represents the induction ability during the junior year. F2 represents the second latent construct, figural relations ability, also during the junior year. And F3 represents the figural relations ability during the senior year. Next, we identify the manifest variables in the model. You'll recall that manifest variables are observable and therefore measurable variables. Now, V1 through V3 represent 3 induction scores during the junior year: induction score 1, induction score 2, and induction score 3. V4 through V6 represent 3 figural relation scores, also during the junior year: figural relation score 1, figural relation score 2, and figural relation score 3. And finally, V7 through V9 represent figural relation scores during the senior year. So V7 is figural relation score 1, V8 is figural relation score 2, and V9 is figural relation score 3. Next, we identify the manifest variables related to each of the latent constructs. The manifest variables that are indicators of the latent construct F1, which is the induction ability during the junior year, are V1, V2, and V3. The manifest variables that are indicators of the latent construct F2, which is figural relations ability during the junior year, are V4, V5, and V6. And the manifest variables that are indicators of the latent construct F3, figural relations ability during the senior year, are V7, V8, and V9. In step 2, we specify an equation for each one-way explanatory predictive relationship in the SEM. And these are regression type of equations. So based on the previous information that we've looked at, equations for the dependence of the manifest variables V1, V2, and V3 on the latent construct induction ability during the junior year, or F1, are as follows. So V1 is related to F1 through the regression equation V1, again, which is the induction score 1 during the junior year, being equal to lambda 1 times F1, which is this induction ability junior year latent construct, plus an error term denoted by E1. Similarly, V2, the induction score 2 during the junior year, is related to F1 through the equation lambda 2 times F1 plus E2, where E2 is an error term. And then finally, V3, the induction score 3 during the junior year, is related to the F1 latent construct via the equation lambda 3 times F1 plus E3. Equations for the dependence of the manifest variables V4 through V6 on the latent construct F2, which is the figural relations ability during the junior year, are as follows. So V4, the figural relations score 1 during the junior year, is associated with F2 in the following way. Lambda 4 times F2 plus E4. V5, the figural relations score 2 during the junior year, is equal to lambda 5 times F2 plus E5. And then finally, V6, the third figural relations score during the junior year, is equal to lambda 6 times F2 plus E6. The equations for the dependence of the manifest variables V7 through V9 on the latent construct F3, which is the figural relations ability during the senior year, are as follows. V7, the figural relations score 1 during the senior year, is related to F3 as lambda 7 times F3 plus E7. V8, which is the figural relations score 2 during the senior year, is equal to lambda 8 times F3 plus E8. And V9, the third figural relations score during the senior year, is equal to lambda 9 times F3 plus E9. In addition, we have equations for the dependence of the latent constructs F2 and F3 on other latent constructs. And so F2, which is the figural relations ability during the junior year, is presumed to depend on F1, the induction ability during the junior year, via the equation F2 equal to beta sub 2(1) times F1 plus D2, and in this case D2 is the error term associated with that model. F3, which is the figural relations ability during the junior year, is assumed to depend on both F1 and F2 according to the equation beta 3(1) times F1 plus beta 3(2) times F2 plus D3, where again D3 is the error term for that particular model. Now note that this structural equation model, this structural regression model, is simultaneously modeling two response variables that are unobservable as linear functions of explanatory variables that are also unobservable. Now, wrap your head around that. Think about that for a few minutes. That is very, very different from any other kind of linear regression model that you've ever seen. In this particular representation, the response variables and the explanatory variables are all unobservable. Step 3, we specify notation and or values for the variances of all random variables in the system, as well as for all covariances of pairs of random variables in the system. So here we have the assumed covariance relationships between error terms, between factors, and between factors and error terms. And so in the first bullet point, you see that we're assuming that the covariance between each pair of error terms is 0. And so that is a constraint that we're going to impose on this model. In the second bullet point, we're not setting the variances of the error terms equal to any particular value. We're defining notation for those variances. And so the variance of E sub I is going to be denoted by theta sub I in this particular model. In the third bullet point, we're assuming that the covariances between pairs of error terms and the factors, the latent constructs, are all 0. And so that is an assumption that, again, is imposed on this model. And you can see here that there are 27 such covariances that are all set to 0 by assumption. And then finally, in the fourth bullet point, you can see that what we're doing here is we're going to set the variance of each latent construct in this model equal to 1. And the reason we do this will be discussed in a future lecture video. In step 4, we identify all model parameters to be estimated. So we have the loadings. These are the slope coefficients on the equations relating the manifest variables to the latent constructs that impact them, lambda 1 through lambda 9. We also have variances of the error terms in the model. Now, there are 9 error terms associated with the regression equations for the manifest variables, E1 through E9. Each one has a variance term associated with it. And so we have those 9 variances. And then we also have error terms associated with the regression equations involving the latent constructs. And so we have 2 of those error terms, D2 and D3, each one having its own variance. And then finally, we have the latent regression slopes. So these are the slope coefficients involved in those regression equations relating the latent constructs. So there are 23 parameters that need to be estimated in order to fit this SEM. And so a couple of questions that I want you to consider. What are necessary conditions for these parameters to be identifiable? And the second question, what conditions will lead to the estimators being reliable? We're going to be discussing both of these questions in detail in a future lecture video, but I wanted to pose those now and get you thinking about these things. All right, and then step 5, we're going to take what we've put together and we're going to construct a path diagram for this particular structural equation model. And so you'll recall that ovals or circles are used to represent latent variables in a structural equation model, and we've got 3 of those in this model. Rectangles or squares are used to represent manifest variables. These are the observable and therefore measurable variables in the model, and we have 9 in this model. Note also that there are 11 error terms in the model, and these are going to be represented in the diagram by their respective letters. So we're going to have E1 through E9, as well as D2 and D3. One-sided arrows are used to represent relationships that are one-way, directional, predictive. Two-sided arrows are used to represent relationships that are two-way, correlative, or mutually impacting. And then finally, the parameters that need to be estimated are going to be indicated by asterisks in the path diagram. So here is the path diagram for this structural regression model. Now let's first identify the latent constructs or factors in this model. Again, the latent constructs are represented by ovals or circles, and so we see that F1, F2, and F3 are the latent constructs in this model. Let's stop a moment and look at the relationships between these latent constructs that are specified by this path diagram. First, we see that because there are one-way arrows emanating from F1 to both F2 and F3, this is telling us that F1 is allowed to impact both F2 and F3 directly via a regression type of relationship. In addition, F2 is allowed to impact F3 in a regression type of relationship because of the one-way arrow from F2 to F3. And because there is a path from F1 to F3 through F2, not only does F1 get to impact F3 directly via the one-way arrow with slope coefficient beta 3,1, but F1 can impact F3 indirectly through the path that goes through F2. Next, let's identify the manifest variables. Now again, the manifest variables are represented by squares or rectangles in a path diagram. And manifest variables are the observable, measurable variables. And so we see here that we have 9 manifest variables, V1 through V9. V1, V2, and V3. The 3 induction scores during the junior year are allowed to be impacted by F1, the induction ability latent construct during the junior year. V4, V5, and V6, which are the figural relation scores during the junior year, are allowed to be impacted by F2, the figural relations ability during the junior year. And then finally, V7, V8, and V9, the figural relation scores during the senior year, are allowed to be directly impacted by F3, the figural relations ability during the senior year. Now, based on this model, V1, V2, and V3 can only be impacted by latent construct F1. Because the arrows emanating out of F1 are one way, V2, and V3 cannot be impacted by F2 or F3. V4, V5, and V6 are allowed to be directly impacted by F2, but because there's a path from F1 through F2 down to those manifest variables, this model allows V4, V5, and V6 to be impacted indirectly by F1. And then finally, V7, V8, and V9 are directly impacted by F3, but because there are paths from F1 and F2 to those 3 manifest variables through F3, V7, V8, and V9 can also be impacted to a certain extent by F1 and F2. Next, let's identify the error terms in this model. In general, there's going to be an error term associated with each regression type of equation in the model. And so if we identify the various response variables that exist in this system of equations, there's going to be an error term associated with each model where each of those variables is a response. And so D2 and D3 are error terms in the regression type of equations relating F2 and F3 to F1 and F2. In addition, V1 through V9, the 9 manifest variables, are response variables. And so there's going to be error terms associated with each of those variables. Now this brings us to identifying the various endogenous variables. You'll recall that the endogenous variables are the variables that are response variables in at least one of the equations in the model. And so again, we have F2 and F3 being endogenous variables because each of those is a response variable in at least one of the equations in the model. And the 9 manifest variables are also endogenous variables because each of those shows up in at least one equation in the model. Exogenous variables, on the other hand, are variables that are never response variables in any of the equations comprising the structural equation model. And so F1 is never a response variable in the model, and so it's an exogenous variable. Similarly, D2 and D3, these are error terms, and so they are never response variables, so they are exogenous variables. And finally, E1 through E9, the error terms associated with V1 through V9. These are never response variables in any of the equations in the system, and so they are exogenous variables as well. And finally, we can count the number of parameters that need to be estimated in this model by counting the number of asterisks we've got here. And we can see here that there are 23 parameters to be estimated in order to fit the model. So that's what I wanted to show you in this lecture video. I'll see you in the next lecture video.